So I'm very pleased to introduce Ian Jauslin. This is his second year here at the Institute. He's well known to many people. He's probably our most interactive member by far, I would say. He is also going to be giving a musical presentation, interlude, after tea with, I think, a member of the physics
Yeah, that's right. He's right there.
Okay, excellent, excellent. Okay, so if you're going to have tea, please join Ian, and I don't know your name, I'm sorry? Ahmed, okay, for a musical interlude. Now, I have a few more things to say about Ian. I need to get my notes out. He did his graduate work in Rome, which is one of the leading centers of mathematical physics, especially for what's called non-equilibrium statistical mechanics and interacting models of electrons or fermions. So he did things which called the Kondo, on the Kondo model, for those of you who are physicists here, and he also worked on graphene, which is a topic which is very hot in the press these days. This is a single layer of carbon atoms, which is supposed to have miraculous properties. Now, before I let Ian start, I would like to tell you something about Ian's personal background. He has French, Swiss, and US citizenship. He actually has 3 passports. In addition to English and French, he speaks fluent Italian and Spanish. So he's a UN all-in-one here. His mother is a mathematician, and his father is a physicist. And they are both professors at the University of Bourgogne in France. Finally, let me mention that this is Ian's last year at IAS. However, he's not going to go far. He has an appointment at Princeton. So he will be hopefully still an active participant in the many activities we have here at the Institute. Today, Ian will tell us about some problems and progress in statistical mechanics. He has a daunting task since, as you see, we have no blackboard, no slides. I would be in a panic in such a situation because as mathematicians, we're all used to having this. When I asked Ian how he would manage, he said, "I enjoy the challenge." So I now present Ian, who will talk about liquid crystals, order upon disorder.
Thank you. Thank you, Tom, for the lovely introduction. I'd like to add, too, that there are no blackboards, there are no slides. When I defended my PhD, I was allowed, I can't lose that.
Okay.
When I defended my PhD, I was allowed to use slides, but there was no blackboard in the room. And I had this surreal event where I had to describe what a parabola was with my hands. It was very fun. So I'll take the challenge. Thank you all for being here. I'm very happy to see so many friendly faces. I'm going to be talking about some work that I did last year. I work in mathematical physics. Mathematical physics means a whole different bunch of things. I'll try to give you a sense of what it means to me in this talk. One thing that you need to know about mathematical physics talks is that everyone in the audience, as soon as you stop understanding what in the world I'm saying, you are encouraged to interrupt and ask questions, make comments, throw things, whatever you want to do. That's what a mathematical physics talk is, and that's what I want today to be. So I'll be talking about liquid crystals. To tell you what a liquid crystal is, I'm first going to tell you what a liquid is and what a crystal is. A spoiler alert, a liquid crystal is neither. But it's still useful to understand the difference. Some of you may be familiar with water. Water is around. Water can come in a whole bunch of different states. It can be liquid. This is what it is at room temperature and atmospheric pressure. That's how you can drink it. Now, if you warm up water, it boils. It turns into a gas, right? But if you cool down liquid water, it freezes, turns into ice. All of those 3 different phases, all those 3 different materials, they're all water. They're just plain water. The molecule that is making up this material is H2O. It's 2 hydrogens and an oxygen. The molecule is the same, and yet you have these very different properties. liquid water, just as gaseous water, flows. If I take liquid water and swirl it around, it'll move. Whereas ice is a solid. Ice can't be deformed so easily. Liquid water is a liquid. Ice is a crystal. They're different. And I want to discuss today why they're different. How do we understand that they are different? Well, from a microscopic point of view, it's all water. It's all water molecules. But the arrangement of the water molecules is different. In a crystal, so in an ice cube, the water molecules are ordered. What that means is that the distribution of the positions of these molecules, the way that these molecules are arranged, is regular. It forms a regular structure. It forms some periodic, simple, regular structure that kind of looks like a cubic stacking of molecules. Now, this is something that I personally find fascinating. If I look at an ice cube, if I look at a really good ice cube, an ice cube that is made of a single crystal, it's going to be about this big. It's going to contain about 10 to the 24 molecules. 10 to the 24 is a number. It's a 1 with 24 zeros after it. It's called a heptillion. It's a trillion trillions. If I were to count all the grains of sand that are on Earth, I would get a number that isn't even close to 1 heptillion. It's a large number. It's a lot of molecules. But in a crystal, all of these molecules happen to be aligned. They're in this regular, simple, aligned pattern, which is rather astonishing. This is what a crystal is. A crystal is a material that has order, in which the constituent molecules have a regular underlying pattern. They're aligned in some way or another. In a liquid, on the other hand, I don't have order. In a liquid, the molecules, they form this amorphous clump of stuff. This is why a liquid can flow, because in a crystal, I have a rigid structure. I have a very regular structure in the position of my atoms, and I can't break this regular structure so easily. If I wanted to deform my ice crystal, I would have to break this regular pattern. In a liquid, I don't have a regular pattern. My molecules can just roll around each other. That's what allows liquids to flow. Now, in short, what I want to say about liquids and crystals here is that liquids are disordered. They form this amorphous clump. It's a disordered object, whereas crystals are ordered. They have this regular periodic order. So liquids are disordered, crystals are ordered. So what in the world is a liquid crystal? Well, a liquid crystal is a material that has order properties and disorder properties at the same time. How does this happen? Well, the liquid crystals that I'll be talking about today, they mostly occur in systems of molecules that are very anisotropic. These are molecules that are shaped like rods. They're long, they're thin, and they're straight. They're straight, long, rigid, and thin. Thin.
How long are they?
Very good question. So, sounds like stand-up now. So there are different types of liquid crystals that exist in the world. Some of them you can create in labs, like the most famous one that people create is called MBBA. It's a few atoms long, so it's going to be a few nanometers long. You have biological objects that behave like liquid crystals. So a rather striking one is a virus called the tobacco mosaic virus. There's no need to be scared. It mostly affects tobacco. It's shaped like a cylinder. It astonishingly looks like a cylinder. And it's about 18 nanometers thick and about 300 nanometers long. So it's much longer than it is thick. 300 nanometers it's pretty small. You wouldn't see it, but it's fairly large as far as molecules are concerned. And you can see microscope images of these things, and they really look like elongated, rigid cylinders. So I'm thinking of a system of rods. My molecules are rods. In a liquid crystal, there is order in the orientation of the rod. So these rods, they have an orientation that tells you in which direction they're pointing, and they have a position that tells you where they are. In a liquid crystal, I have order in the orientation, which means that if I take a liquid crystal, the rods of the molecules that make up the liquid crystal are going to be mostly aligned. If I tell you the direction of a molecule out here, it'll tell you the direction of a molecule out there. That's order in the orientation. But at the same time, I have disorder in the positions of the molecules. If I just looked at where the molecules are and not which direction they're pointing, I would get this amorphous clump. And this makes for interesting properties. So liquid crystals have non-trivial properties. They flow like liquids because the positions are not ordered, so they can move one with respect to another. And so if you look at a liquid crystal in a lab, it looks like a liquid. It forms drops, and these droplets can merge with each other. But at the same time, I have order in the orientation. The order in the orientation translates to non-trivial optical properties. Liquid crystals have non-trivial optical properties. And I want to give you a trivial example of that. I have a liquid crystal here. I got this off Amazon. It's a coaster. I keep this in my office. It's brown. It's mostly brown, darkish red. This consists of a thin film that is a liquid crystal. It's a so-called chiral pneumatic liquid crystal. It's not so important. What is important is that the molecules in this film, they're oriented in a certain way. And the orientation of these molecules determines the color of this object, which right now is brown. Now I can change the orientation of these molecules by changing the ambient temperature. And I can do that by, say, placing my hand on it. My hand is warm. And so the ambient air is cold. It's not my fault. So you see, the color changes if I warm it up. So it goes to a blue. If you really push it, then it turns back to black. So by changing the temperature, I'm changing the orientation of the molecules. By changing the orientation of the molecules, I change its optical properties. Namely, in this case, I change the color. Okay, that's nifty. You can make mood rings like that. You can make a little bit of money. Now, the optical properties of these liquid crystals have made them very useful in a much more lucrative domain of technology, namely display technology. Many, many displays are based on liquid crystals. This started a while back in at least the 50s and 60s with digital wristwatches. The screens, the little dials on digital wristwatches, they're based on liquid crystals. Same thing for pocket calculators or for Game Boys. I don't know if there's anyone in the audience of the right generation to know what a Game Boy is. I certainly do. And more recently, flat-screen computer monitors, flat-screen TVs, smartphones, they're all based on liquid crystals. In fact, if you've gone shopping for a TV lately, the term LCD, which you may have heard, LCD stands for liquid crystal display. An LCD works with liquid crystals. So they've been used in all these cool and important applications. And it's therefore, well, okay, it's a big therefore, but I'm still going to say it's therefore important that we understand how a liquid crystal works, what a liquid crystal is, and why is it the way it is. Now I'm going to take this question and reduce it to its simplest form. Try and look at the simplest question I can ask to try and understand what a liquid crystal is. So, and what I want to do in that aim is to ask the question, well, why does a liquid crystal exist? Or maybe a more appropriate question would be, how does a liquid crystal exist? More specifically, can I find a mathematical model, some sort of mathematical description that will describe molecules that are shaped like rods, in which I find that these molecules happen to align, and yet don't have any positional order? Can I find a model in which I can prove that this picture that I told you about earlier is true? This, it turns out, is a difficult question. So far, as of yet, we don't have a model for the molecules in a liquid crystal that looks realistic in some sense, for which we can prove that this alignment that I was telling you about occurs. There is no such model. We do have partial results, and I just wanted to mention the reason that I'm here giving this talk now is so last year I was working on such a model. We looked at a model that was introduced in 1979 by a chemist named Ole Heilmann and a mathematical physicist named Elliott Lieb. This is a simplified model for what the molecules in a liquid crystal are doing. It's way simpler than what is going on in real life, but it's something that we can manipulate. And in the fall, we finally released a proof of the fact that in that model, you do have a liquid crystalline phase. This is actually particularly relevant because we got referee reports a few weeks ago, and we just sent the revised version yesterday, so this is very active research. And so now I wanted to make this more of a discussion. So at this point, I'm going to stop talking, and I'm going to let you guys do some of the work for me. Thank you very much.
Could you tell us more about your model, building your model?
Yes.
Say more,
there
please.
you go. Yes, okay. So I told you that a liquid crystal is a system that is made of molecules that are elongated, so they have an orientation and they have a position. The model that we're looking at is, first of all, a two-dimensional model. This is similar to what was being described here, the setting where the anyons exist. So it would be a model that lives on a surface. Okay? In this model, I have little molecules. These molecules, they're represented as little sticks. They're either and these little sticks, and this is the important part, they can only have one of two orientations. They can either be vertical or horizontal. So they have an orientation. The orientation is either a vertical one or a horizontal one. But this orientation is a much simpler one than what you would expect in the real world. In the real world, you would have a rod that can take any orientation that you could possibly imagine. In this model, there are two orientations. That's that's the drastic simplification that allows us to actually prove something about it. So you have these little sticks. They live on a two-dimensional plane. They can either be horizontal or vertical, and they're magnetized. They're little magnets. These little magnets, they like to be aligned with each other. Okay? You've all seen magnets. If you take two little magnets that are shaped like sticks and you put them next to each other, they might be happy. If you put them like that, they won't be happy. They'll want to align. This is the type of system that we're looking at. Yes?
Well, you say the liquid crystals flow like regular liquid. Do they flow the same way in all directions?
No. That's a very good question. You can find some truly nice videos about it. So these are rods that are mostly aligned. So if you're flowing in the direction of the alignment, you have a much more fluid behavior than if you're flowing against the alignment, if you're flowing perpendicular to the alignment. Now, you can actually find some really cool videos on YouTube of this sort of flow. If you look for something called an active pneumatic liquid crystal, because there are liquid crystals that are made of biological entities that are powered. They're little motors that like to move against each other. And you can see them flowing and then getting into traffic jams and breaking the traffic jams and flowing back out. And yes, so the flow in those systems is mostly in the direction of the molecules, and the flow in the direction of the molecules is favored, absolutely. Yes, Jean-Louis.
Thank you. Jan, I have a question. You mentioned that a realistic model, if I'm not mistaken. So if we consider that this model cannot be found in the real world, what do you mean by realistic?
Right. What I mean by realistic in this case would be a model in which the orientation of my molecules is continuous. Any model in which the orientation of my molecules is continuous, and yet my molecules still have a position, if I had a model like that in which I can prove a liquid crystal phase, I'd personally be happy. I would be satisfied with the state of affairs. So this is a rather old theory. There's a seminal paper from 1949 by a guy named Lars Onsager. He's a physicist. He got a Nobel Prize for totally unrelated reasons. He was looking at a model of molecules which have any orientation you could possibly imagine for them. They have any position you could possibly imagine for them. And they interact. But that's pretty much it. So they're cylinders that are not allowed to overlap. They're not allowed to occupy the same position in space, but that's it. someone could prove a liquid crystalline phase in that sort of a system, which is a very simple system, that would be great. That would be very satisfying.
Is there a dual material in which the positions are regular and the orientation of the rods is arbitrary?
That's a wonderful question. Yes. Yes. Yeah. So, okay. You remember those VHS tapes? They had a band in them, a magnetic band. This magnetic band is actually made of a regular arrangement of little, what are called magnetic moments? They're little. Okay, so think of this band as being a two-dimensional regular array of little arrows, where the arrow represents a little magnet. Now, if you take this sort of a model here, where you have these magnetic objects, these little magnets, they exist in nature situations where these magnets, they form a regular pattern, and yet the orientation of the magnets is random. That would be up-down, but you can make it a Heisenberg model and make it a continuous orientation, which in a high-temperature phase would have random orientations, yes. Like VHS cassettes, which, interesting, yes. Yes, Juan.
Is the phase transition between the high temperature and low temperature second order?
Yes, there is a phase transition. So for the model that I was mentioning right now, which would be the Ising model, there is a phase transition, which is second order. For the liquid crystals, there is a phase transition that is first order. So let me explain why this is important. I talked about water earlier. Okay, I'm going to try and keep this short. I talked about water earlier. Water freezes. We all know this. Water freezes at 0 degrees Celsius. You may have heard that too. This is a rather astounding thing. It freezes at 0 degrees Celsius. At 0 degrees Celsius. It doesn't freeze starting at 0 degrees Celsius. It doesn't freeze at minus 10 degrees Celsius. It freezes at 0 degrees Celsius. There's something very special happening right there at 0 degrees Celsius where the water is actually freezing, where the properties of the water are changing in a drastic way. And in fact, if you look at how the properties of water are changing, for instance, what do I mean by the properties are changing? Well, liquid water is very different from solid water, from ice. Liquid water is for instance, denser than ice. Ice floats, because ice is less dense than water. If you look at the density as a function of temperature, the density above 0 degrees Celsius is about 1 gram per cubic centimeter. The density below 0 degrees Celsius is, I think, 0.92 grams per cubic centimeter. And there's a discontinuity there. There's a jump there. That's because there's a transition. There's something very non-trivial going on there, and it's a first-order transition that makes it a jump. So liquid crystals, they behave in kind of the same way. They have a first-order phase transition. They have a discontinuous behavior as this alignment occurs. Yes? Yes?
Can you speak to disciplines of knowledge, perhaps? So we know that liquid crystals are used in TVs, smartphones, et cetera. Someone, I'm assuming engineers or someone figured out within a discipline of knowledge how to do that and how to make them work. What do you gain by understanding this within mathematical physics?
Tough question. So there is, it's all based on hope, really, I think. So there is this hope that if you understand how something works, then you might be able to do something that you didn't think about before understanding how it works. In this case, it's somewhat removed because everyone knows how liquid crystals work. I mean, everyone knows that the mechanism that is making them align is because they're interacting with each other, and there are a bunch of them, and they all want to be aligned, so they're aligned. What mathematical physics brings to that is to actually prove that this picture that we all know is true is actually true. So it's kind of it's in a sense it's an integral part of the scientific method. The scientific method is telling me, okay, so I have this phenomenon and I want to understand it in a systematic way. Well, part of that is going to be, okay, I come up with a mathematical model and I need to understand that really that mathematical model contains the behavior that I think it should, that I think is the behavior that is observed. So in that sense, it's necessary. It's a necessary part to claim that you're done, that you really understood how this thing is working. Now, from a practical point of view, understanding, being really certain why liquid crystals are the way they are might not be all that important if what you want to do is build a screen. Also, I might want to mention that LCD screens are on their way out, so this is not a horse you want to jump on at this stage. Yes, John.
Your picture of these rods lining makes it hard for me to understand how, when you warm up your coaster, all the orientations change.
Yes. I cheated. What I described with the rods lining up, that is called a pneumatic liquid crystal phase. Those of you who know Greek might know what pneumatic means. I personally don't. So that's a pneumatic liquid crystal phase. Everyone's aligned. In this little coaster here, I have what's called a chiral pneumatic liquid crystal phase. This is how a chiral pneumatic liquid crystal phase looks. It's made of successive planes. It's a stack of different planes. In each plane, my rods are aligned. Okay? But in different planes, the alignment is different. The way that in that material this is carried out is I'll have one plane where the rods are aligned in this direction, and the next plane they'll be slightly rotated, and then the next plane is slightly rotated, and the next plane is slightly rotated, etc. And so you have this rotation here. It forms this helix structure, which is where the chirality comes from. The color is determined by the distance. So I have these planes that are rotating like this. The distance that it takes for me to come back to the original orientation, that will determine the color. And this length there, this length scale, depends on the temperature.
Okay, I think maybe it's time, unless there's some other pressing questions. Yes? Okay. Okay, I just have one final comment. When my son's about your age, and he used to have these little cars, little metal cars, which had some very interesting kind of paint on them. And when you put them in cold water, they'd be one color, and you heat them up, and they'd have another color. If I can find some, it's still left over in the basement, I'll bring them to you.
Yes, please do. Thank you.
Okay, thank you.
Thank you very much.